Hi there. In this video, what we're going to talk about is the calculation of pH for two different types of solution. The first one is the strong acid like hydrochloric acid or nitric acid. Then we'll look at calculating the pH for a strong base such as sodium hydroxide or potassium hydroxide. The calculation of pH for these types of solutions is rather simple. All you have to do is calculate the amount of hydronium or the amount of hydroxide, respectively, from the strong acid or the strong base. It's rather simple type of calculation. So let's begin by taking a look at, again, our definition. If you want to have the This is, by the way, section 16.4, strong acids and strong bases. So an acid, what it does is it reacts with water to form the hydronium ion and whatever the counter ion is, the anion, right? So the idea is that if something is an acid, it will react with water. It'll donate the H plus to the water, giving you hydronium, right? So you can think of hydronium as essentially H2O attached to H plus. I know that's not the actual structure of it, but that's essentially the way you can think of it. It's a water with an extra H plus on it. Okay, so that would be the hydronium ion. So the acid, you can think of the acid as just like an H plus A minus, almost like an ionic compound, even though it's in generally acids are really thought of as molecular compounds. You can think of it as H plus A minus. So then you react it with the water, and what happens? Essentially, the A minus donates the H plus to the water. So now you have the A minus, and now you have the H2O H plus, which is really the same thing as hydronium, right? 3 hydrogens and a positive charge. Okay, so that's our, again, that's what's called the Bronsted-Lowry acid, right? We call that Bronsted-Lowry. This is the acid. Remember, the one that accepts the H plus is called the base. So this is a Bronsted base. The products, one of them is an acid and one of them is a base as well. So this one we're going to call the Bronsted conjugate acid, right? The conjugate acid is the base with the extra H plus. So base conjugate acid, and this is the conjugate base, right? So the conjugate base is essentially the acid minus the H plus. The conjugate acid is the base plus the H plus. I make sure I said that right. The conjugate base is the acid minus the H plus. Okay, so acid conjugate base, they differ by an H plus. The base and the conjugate acid are really the same substance, just one of them has an extra H plus. The acid is the one that has more H plus. So the conjugate acid is the base plus an H plus. Okay, now here's what happens with strong acids. Weak acids are different, but for strong acids, what happens is we get what's called 100% ionization. It's not really 100%, but it's close enough that we'll just treat it so. So the idea would be, let's say hydrochloric acid, that's a strong acid. Put it in water. What happens is it donates the H plus to the water, so you get chloride, and you get hydronium, right? So I'm going to make up a number here. Let's say that we have, 0.8 moles to start off with. This 0.8 moles will react with water. We'll assume water is the excess reactant. It's the solvent, so there should be a lot more water than acid. So what happens then is you're going to lose all of the reactant here. This is going to go down by 0.8 moles. This will go up by 0.8 moles. I hope you sort of see the relationship, right? That's the idea of a chemical reaction, right? Is that you lose reactant and you gain products. It's transformed into the products. So these are going to go up by 0.8 moles. Now the water will go down too, but there's so much more of water that doesn't matter. We don't need in our calculations, okay? So once it's over, this is 0, and this is 0.8. And this is 0.8. So the point that I'm trying to make is that the amount of hydronium that you end up with is equal to the amount of acid that you put in. So if I put in 1 mole of acid, I'm going to get 1 mole of hydronium out. That's, in a sense, the definition of a strong acid, is that the concentration or the amount of the hydronium ion that you get at equilibrium is equal to the initial concentration of the acid that you put into the water, that you produce with the water. So that's kind of cool. It makes the calculation very easy. Why? pH is just a negative log base 10 of the hydronium concentration. Now this is moles, so we would need to divide that by volume to get molarity. Remember, this is the concentration. But that makes things so easy. What it means is if I tell you, you've got a 1 molar HCl solution, the hydronium concentration is going to be 1 molar. You don't have to do any kind of fancy calculations with that. Okay, so let's remind ourselves what the strong acids are. Generally there's like 7 or 8 of them: HCl, HBr, HI. Okay, then you have, so those, are 3 of them. I'm going to put a different row here, a different column. HNO3 is another common one. H2SO4 is another common one. By the way, hydrogen, there are 2 hydrogen atoms in H2SO4, sulfuric acid, that's called. There's 2 of them. Only one of them is a strong acid. Okay, the other one is a weak acid. And then you got your HClO4 and your HClO3, and I think that's all of them, right? 3, 5, 7. So there's 7 strong acids there. There are also compounds called superacids, which are even stronger, but we're not going to worry about those for this course, okay? So all of those will go to 100% ionization. So let's take a look at an example problem. Okay, calculating the pH of a strong acid solution, a chemist dissolves 299 milligrams of pure nitric acid in enough water to make 280 milliliters of solution. Calculate the pH of the solution. Round your answer to 3 significant decimal places. Okay, so notice they give you the mass here. They give you the name of the compound, the acid, but not the actual formula. That's nitric acid. And then they give you the volume in milliliters. Okay, so let's go through this problem. This problem is they're making you do a couple of extra steps because they felt like if they just give you the number of moles of nitric acid, it'd be a little too easy for you to do. Okay, so let's take a look. 299 milligrams of nitric acid, 280 milliliters of solution. Calculate the pH. So it is a strong acid. Nitric acid is a strong acid. HNO3. Okay, so 299 milligrams of HNO3. Okay, well, let's convert it into, I'm going to convert it into millimoles. Okay, so let me do it this way. I'm going to multiply this by 1 mole of HNO3. And I'm going to divide it by the molar mass. So hydrogen has a molar mass of 1.01. Nitrogen has a molar mass of 14.01. So that together is 15.02. Oxygen is 16.00. So there's 3 oxygens. So that's 3 times 16, which is 48. So 48, 58, 63, I guess it is. 0.02 grams. So that's the molar mass of HNO3. Divide by the molar mass. Now look at the way I did this. I have milligrams here. So here's what's going to happen. The grams are going to cancel You're going to have moles here, and then you're still going to have milli. So you're still going to have milli. So 299 divided by 63.02 is 4.7445. I'm keeping a couple of extra significant digits for this intermediate step. You're going to have a milli there. So don't forget the milli, and then you got moles. You have millimoles. Remember, milli is 10 to the minus 3. Okay, 10 to the negative 3. Now, to get molarity, that's moles over liters, right? Those are the units of molarity. But look what happens. If I have millimoles and I divide that by milliliters, the milli are going to cancel and you're going to get moles per liter. So the reason that I didn't convert the milligrams of HNO3 into grams of HNO3, which I could have, and then divide it by the molar mass to get the number of moles, is that I also know that our volume is in milliliters. Okay, so I now can see that our molarity of HNO3 is moles, so 4.7445 millimoles over volume, 280 milliliters. And look what happens to the milli. Okay, so if I divide that by 280, I now get 0.01694 molar, capital M for molar, right? Now you very well could have converted milligrams into grams by dividing by 1,000, and then converted milliliters into liters by dividing by 1,000. So you would have two numbers that are smaller by 1,000. You'd have 0.0047445 and 0.280. If I'd done the conversion, we would have had 0.0047445 moles divided by 0.280 liters, and that would give you the same answer. Okay, so there's your whatever, whichever one you want to use. Sorry, 01694, 01694. I forgot the 4 there. That's what happened. Okay, so either way you can do that. Just use your dimensional analysis to figure out what it's going to be. Now we want to find the pH, right? So we have a concentration 0.01694. Let's find the pH of that solution. Well, it's a strong acid. So that means the concentration of hydronium is the same as the initial concentration of the acid. 0 for initial, right? We use that in kinetics. So there we go. We have the concentration. So the pH is just going to be the negative log of 0.01694. Okay. So if you take the negative log of that, you get 1.771. They just want 3 significant digits. Well, actually, they said 3 significant digits. So I guess 1.771 would be the answer. I think they really mean 1.77, but who knows? Okay, one or the other. All right. Let me do. There we go. Okay, so let me show you on my calculator here. So we had, oops, sorry, 0.0169447. Want to find the pH, take the log, change the sign, 1.77 or 1.771, and there you go. Okay, so that's finding the pH of a strong acid. Now, what we're going to do is we're going to move on. See how easy that is? All you got to do is just find the molarity of the acid, and that is the hydronium concentration. When you do weak acids, it's more complicated because you have to take equilibrium into account. Let's see here. Okay, yeah, they're all pretty much the same. Okay, so the next issue are the strong bases. So we're gonna do a calculation of the pH of a strong base. Here we have to do an extra step. And I'll show you how to do that in just a moment here. There we go. Okay, the strong base. So let's take a look at this. So the strong bases kind of similar to the strong acids, but let's go over which ones they are. So you have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. By the way, these are the two most common right there. These other three are considered strong acids, but they have interesting chemistry. It's a little different, but in any case, those are the category. And then what happens is magnesium hydroxide, you would think it was a strong base, but it turns out it's not because it's just not that soluble. So that's not included. Sometimes calcium hydroxide is included, but to be honest with you, it just depends who you talk to. Some people will include calcium hydroxide, some will not. So I'll put a little asterisk there. Again, it's the issue of solubility. Then you have strontium hydroxide, and this is generally considered a strong base. So, that's one, and then barium hydroxide. Now, these are interesting strong bases because there's two hydroxides, so they give you twice as much hydroxide in the solution. So it's generally considered these five, and then for sure these two. Again, it comes down to solubility here. Are they soluble? Okay. This one's just not that. It's insoluble in water. Okay, so if it's not soluble, it can't form hydroxide. That's the problem. Okay, so now here's what happens. I'm going to use sodium hydroxide as an example. Suppose I take 1 mole of sodium hydroxide and I try to dissolve it into 1 liter of solution, 1 mole divided by 1 liter. It's a solid, by the way. If you put it into a liter of water, it just dissolves completely, and you get 1 mole of sodium and you get 1 mole of hydroxide, right? So it all dissolves. So it's kind of like the strong acid. Whatever you put in, that's what you get out. And there's our hydroxide. So what we can do is we can say the concentration of hydroxide is equal to the initial concentration of the base. Okay, so if you know the initial concentration of the base, you know the concentration of the hydroxide that forms from it. With the exception here, with these ones, you get 2 to 1. So for column 2 or group 2A, so this is group 2A, the concentration of hydroxide is actually the 2 times the initial concentration of the base. Is twice as much, right? Because it just dissolves into 2, right? You get barium plus 2 hydroxides. It's twice as much hydroxide. You get the same amount of metal, but you get twice as much hydroxide. Okay. So what we can do then is we can do a pOH calculation. Negative log of the concentration of hydroxide. That's the pOH. And then we use this little relationship here. Remember this, pH plus pOH is 14. So if we know the pOH, we can find the pH from this relationship here. The pH is 14.00 minus the pOH. Very simple. Okay. So let's take a look at an example here. That this is the equation from the earlier section. So is this one. And then this is the new information here. Okay. Okay, so this one's going to be very similar to the strong acid problem. They're going to give you the number of milligrams of the base. They give you the name of the base, so you have to figure out the formula. And then you're going to divide that by the volume, which is in milliliters. That'll give you the molarity. From that, you can calculate the pOH, and then from the pOH, you can find the pH. So let's read it. is calculating the pH of a strong base solution. A chemist dissolves 224 milligrams, that's a mass unit, of pure barium hydroxide in enough water to make 90 milliliters of solution. There's your volume. Calculate the pH of the solution at 25 degrees C, okay? So 224 milligrams of barium hydroxide and 90 milliliters of solution. So 224 milligrams of barium hydroxide. Remember, if it's in group 2, you're gonna have 2 hydroxides in 90 milliliters solution. Okay, so again, I hope you understand the difference between mass and volume, right? You're weighing out 224 milligrams. That's approximately the mass of an ibuprofen tablet, Advil. Not the prescription kind, but the kinds you get from the store. We're going to dissolve it into 90 milliliters of solution. Okay, so you're going to dissolve it in there. It's going to dissolve. Barium hydroxide is soluble in water, so you're going to get hydroxide in there. But remember, since it's barium hydroxide, you're going to get a barium. We're not concerned about the barium in this problem, but we are concerned about the hydroxide. So you get twice as many hydroxides. So if I were to put the hydroxide in red and the barium in blue, you would have twice as much hydroxide, twice as much red as you have blue because of this 2-to-1 relationship. Okay. So there you go. So we're just going to find the concentration. So the goal is find the concentration of hydroxide. Okay, so we have 224 milligrams. So here's what I'm going to do, just like the previous example. 224 milligrams barium hydroxide. I'm going to convert it into moles. So 1 mole of barium hydroxide is, now how much does that weigh? Let's see. Barium is 137.3. Oxygen is 16.00, but there's 2 of them, so that gives you 32. And then hydrogen is 1.01, but there's 2 of them, so you get 2.02. So that's 34.02 plus 137.3. It might be 3.1, I'm not sure. 231,671. So 171.32 grams. Okay, so what's going to happen is the grams will cancel, but not the milli. You're still going to have your milli and you're going to have your moles. Milli times moles is millimoles. Okay. So 224 divided by 171.32. And it looks like you got a little over a mole. So you have 1.3075 millimoles of barium hydroxide. But be careful, because that's not the hydroxide, that's the barium hydroxide, right? This is the molar mass of barium hydroxide. If we want to know how much hydroxide we're going to get, one of these gives you 2 of those. So we're going to multiply it by 2/1, right? And so times 2, you get 2.615 millimoles. Sorry, I keep forgetting the milli, right? Of hydroxide. That's to get the hydroxide. It's 2 hydroxides for every 1 barium hydroxide. Okay, 2 wheels for every bicycle. So now we have the number of millimoles. We also have the milliliters, 90. Right? So the molarity of the hydroxide is the number of millimoles of hydroxide divided by the number of milliliters, because the milli is going to cancel. 2.615 millimoles over 90 milliliters. And you get 0.02906. Again, the milli cancel, so you're with moles per liter. If you want to, again, you can convert millimoles into moles and milliliters into liters. You're going to divide them both by 1,000, and you'll get the same answer. So now we can calculate the pOH. Negative log of 0.02906, right? That's how we calculate the pOH. It's the negative log of the hydroxide concentration. 1.537, which means it's pretty basic. The lower the pOH, the more basic it is. But we don't want to know the basicity. We don't generally look at basicity. We look at acidity. So for that, we want the pH. And the pH is 14 minus the pOH. So you get 12.46, 2 significant digits, right? The 12 is a placeholder, powers of 10. The 4, 6 are the actual significant digits, okay? So very basic, right? Remember the scale? It's easier to forget the scale, but the scale is, you know, for pH, you know, 7 is neutral. Less than 7, you know, down to like -1 is acidic. And then above 7, like let's say up to 15, is basic. So 12.46 is way up there in the basic solution, okay? So there you go, 2 solutions that you need to be able to calculate the pH for. Strong acid, strong base. In these problems, they kind of give you a couple of little, you know, a couple little things in terms of the units. They give you milligrams, so you have to convert that to millimoles and then divide that by the milliliters to get the molarity, because it's the molarity that matters. And then for the strong base, you have to take into account that the second column, the group 2A, you can have twice as much hydroxide as you have of the salt. That wouldn't be an issue for lithium or sodium or potassium hydroxide, right? So there you go. Next up is we'll deal with the weak acids, and then after that we'll deal with the weak bases in the separate videos. Take care.